Okay. The first thing I want to talk about is um, how to make the most of your studying to help you with actually improving your score. So the way the GRE works, it's kind of true of other standardized tests, but it's more true of the GRE than in the GMAT than other ones where just knowing the underlying math isn't necessarily enough because they'll ask you to answer questions in ways that you're not used to doing in math class and that you probably weren't doing for homework. And so the Manhattan 5 pound book is a good intermediate step. The GRE math review PDF, that's a good starting step. But really the only way to get a sense of what the ETS is going to throw at you is to do a bunch of ETS questions. And it's easy to say, hey, do a bunch of questions and it'll help you. But you also want to look at it a certain way. They're all designed to minimize calculation. And so there's a textbook way to solve every question, but that isn't always the best way. And also, it isn't the most obvious way every time. And so what you guys want to do is to work on a lot of, workbook ETS questions and to try to solve them in more than one way. There's going to be a textbook way that your math teacher would show you, but there are going to be shortcuts based on things like number properties and kind of the reasoning that we talked about for quantitative comparisons. And so just because you can solve a question one way doesn't mean you're done with it. Doesn't mean you've extracted every insight that you can. And one way that I would put it is if you knew 3 ways to answer 50 quant questions, that's probably better than one way to answer 150, because it means like you can break the problem down, you can see the parts of it, you can see like what are the cues that I can do certain things here. And so when you start off, it's initially it's like, okay, I got to remember some rules for math. I don't know, you know that's where you got to start because you don't remember the Pythagorean theorem or something like that. um, but as you get better with the fundamentals, then you want to work on converting that to getting answers right on the test, and playing around with answer or with questions and answering them in different ways. That's going to be the way that your score changes. Another thing I'm going to say is that the geometry and data analysis, for the most part, they always have algebra and arithmetic mixed into them. So there are a ton of data analysis questions that are just percent change. There are a ton of geometry questions that require some algebra to solve. And so you use some geometry rules to set them up, but you use some algebra to actually solve for the answer. And so it's not like arithmetic and algebra, we're done with those. It's more like geometry and data analysis are ways to set you up to do arithmetic and algebra problems. One exception, there aren't that many, but one exception would be some of the standard deviation and normal distribution questions. Those don't really have a lot of algebra and arithmetic correlates there, although we did do one um, last week that had something like that. So you just want to be aware of that. Okay, so let's get started on geometry. And share screen. Okay, so quickly, I'm just going to go through some rules. You guys are going to have this in the PDF and then in the video so you can come back to it. I just want to introduce you to the rules so you know they're there. So first, we're going to go over some triangle stuff. These are things that you want to know, and not only know as in like if I ask you about them, you could answer, but notice, like visually be able to notice. And so we have some right triangles. A right triangle just means there's a right angle. And the way they show that is a little square here. And one triangle you want to notice is a 3, 4, 5. The hypotenuse is 5. One of the two legs is 3 or 4. So that if you saw something like this, you say, oh, I know what to do. Or you see something like this, you say, oh, I know what to do. Another issue with that is it could be 3, 4, 5. It could be 6, 8, 10. So it could be doubles of this. It could be 40, 30, 50. So you just want to train yourself to see that. This is probably the most common right triangle that you'll see of the ones that aren't just a random right triangle. So this is called the Pythagorean triple. The next most common, but also still not that common compared to the 3, 4, 5, is the 5, 12, 13. So it does come up. This is maybe when you see a Pythagorean triple, 60% of them at least are this, and then maybe 10% are this, and then the other 30% are like all kinds of different values. So it's really worth it to notice these. And then we have special right triangles. Special right triangles have ratios that come from their angles that tell you what all the side lengths are, where if you know one side length, you know all three. So let's start with the 45, 45, 90. The way that we see this one set up is that oftentimes it's a square that's cut diagonally. And what happens is you get a 45-degree angle here, 45-degree angle here, and then you have your 90 here. What that means is since it's a square, these sides are the same. And we can use the Pythagorean theorem to solve for this side here. X squared plus x squared equals this. So we'll call that c squared. And then you get 2x squared equals c squared. You square root it and you get x root 2. You want to see that one. That one comes up a bit. The one that comes up probably even a little more than the 45, 45, 90 is the 30, 60, 90. The way they can hide that one is an equilateral triangle. So everything is 60 degrees and all the sides are equal. You split that down the middle and you make a 30, 60, 90. The short side is opposite the 30 because 30 is the little angle. So the opposite side is going to be the little side. That'll be x. You double it to get the hypotenuse. So 2x. And then the little side, you multiply that by root 3. Root 3 is about 1.7, 1.8 around there. And that's how you get this medium side. So again, you want to notice that one. Other triangle stuff, the area is 1/2 base times height. If you think about it with any rectangle, the triangle is just half that rectangle. And so it's base times height is the area of your rectangle. Cut it in half to get the area of your triangle. Isosceles triangle, this means you have two sides are the same or two angles. If they tell you the sides are the same, then they're probably going to want you to notice the angles are the same, the base angles if the sides are the same. And so if they tell you the angles are the same, then you're going to have to know that the sides are the same. So they kind of either go from sides to angles or angles to sides. Then we have some angle relationships. So let's start with the supplementary ones. These add up to 180. You have a linear pair here. So x and y. If you see this baseline here is a straight line, x plus y equals 180. Now that's true whether it's two angles or whether it's three. So you could have a linear triple, x, y, z, still 180. X plus y plus z is 180. You also have the interior angles of a triangle. The inside of a triangle adds up to 180 degrees. Then for congruent angles, we have alternate interior angles. So interior in between the two lines and alternate on other side of this transversal, this line. Really what you need to know though is that it's a z or a backward z. If these lines are parallel and you've got a z, then you have alternate interior angles. The insides are congruent, the inside corners of the z's. Vertical angles look like an x. So these two angles here are congruent. But these two angles are also congruent to each other. So look for the x. Corresponding angles, do you see how this angle here is the upper left of these four? This angle here is also the upper left of those four. So like upper lefts, as long as the lines are parallel, upper lefts are congruent to each other, lower rights are congruent to each other, and vice versa. Between these, you can pretty much do most of the geometry stuff you need for the GRE. And then our last little thing of rules, exterior angles. All polygons just mean, shapes with many sides, their exterior angles add up to 360. So a triangle has 3 exterior angles, 1, 2, and 3. So each one's 120. A rectangle has 4 exterior angles, and they add up to 360 again. So 90, 90, 90, 90. If we had a decagon with 10 sides, each angle would be 36 degrees, assuming it's a regular. So this is a regular polygon means each side is the same length, because otherwise this might not be 120, 120, 120. You could split them up different ways. Although the exterior angles, the angles on the outside always add up to 360. The interior angle rule is a little bit different. You can memorize a formula, which is n minus 2 times 180, where n is the number of sides of the polygon. But another way to think about it is just you have 180 degrees on the inside of a triangle, and every time you add a side, you add 180 degrees. So if we go from 3 sides to 4, we add 180. You add another side, so we go from 4 to 5, you add 180. We go from 5 to 6, you add 180. The last two geometry things, we've got the midpoint formula and the distance formula. Now, I actually advocate not learning them as formulas because you kind of already know them. So the midpoint formula is just a fancy way of saying average the x coordinate, average the y coordinate, and that's where your midpoint is. So the average of 1 and 3, well, let's find out. 1 plus 3 over 2, so 4 over 2, that equals 2. And then the average of 2 and 4, 2 plus 4 over 2, 6 over 2 equals 3. The midpoint of these 2 points is 2, 3. So the midpoint formula is just the average. So you average the x coordinates, you average the y coordinates, and that's your midpoint. There's a formula for it, but I feel like that just confuses things more than knowing that you average them. The distance formula is just the Pythagorean theorem. It's just a squared plus b squared equals c squared. Well, how do I do that with these 2 points? How do I figure out what that means? I just turn them into a right triangle. So I go straight down, straight across, and then I connect my hypotenuse. Now, what's the distance up? Well, I look at my y coordinates because y coordinates are vertical, right? I'm going from 2 to 5, so that's 3. The height's 3. And then in my x coordinates, this x coordinate here is a 1, this x coordinate here is a 3, so I'm traveling 2 units. So then I do 2 squared plus 3 squared equals c squared. 4 plus 9, 13. Square root both sides. C equals root 13, which is a little bit less than 4. A little more than 3, a little less than 4. So instead of thinking of the distance formula as its own thing, just remember it's the Pythagorean theorem. All right, let's get to some problems. This is page 88 in your workbook. This is the in the geometry chapter. Do you guys notice anything about this triangle? Carson?
It should be the like 5, 12, 13, right?
It could be. I wouldn't say should be, but it could be, right?
Right.
And what would we do to make it a 5, 12, 13?
You would set x equal 90.
And y equal to 0, right? Because then we have a 5, 12, 13. So we know that's a solution right now. We know that is a solution, right? So that's actually nice. When you get that the values are equal on the first thing you try, that really narrows it down because then you know your answer is either C or D. And all you need is one more example of them not being equal to get to know that the answer is D. Does that make sense? Like strategically, by getting C, that means that it's either this or this. And when you have something, when you have a one solution that's equal, almost always what that means is you're going to either have they're always equal or they're equal exactly once, and every other set of numbers you try, they're not going to be equal, and the answer is D. So it's kind of, when you get that they're equal, when you get quantity A and quantity B showing up equal, that's a pretty easy thing to check. So at this point, I'm not worried like, oh, I've got to pick the perfect numbers to try for Y or for X. I'm going to say this. I don't want to try X right now. I want to try Y, because if I try X, I'm going to have to do trig. And our calculators, the GRE calculator, does not have trig. So that's going to be messy. So what I'm going to do is do things here and then think about what that does to the angle X. Okay? Does anyone want to volunteer for a number that we should try for Y? Nope. Okay. So at this point, what I would do is say, you know what? We tried this. We're going to set up the Pythagorean theorem here. And so it's this squared plus this squared equals this squared. Now, if you don't know your squares up to 13, it'd be nice if you did, but it's not the end of the world. You get 169. And then we have 5 plus y times 12 minus y. At this point, then, what you can do, and this is the textbook way, and this is why I don't want you guys to always do the textbook way. I'll show you real quick, but it would take a long time. We FOIL this, and we're going to get 60 plus 7y minus y squared equals 169. Yeah. And then we've got to like solve all this and refactor. So let's put this over here, and we want y squared to be positive, so we'll put that over there. So we're going to add y squared to both sides and subtract 7y and subtract 60. And so then we have this, and then we have to use our factoring rules. And so then we get what multiplies to 109 and adds up to -7. Let's see. Oh, nope. I wrote this down wrong. That's why it looks crazy. Sorry. It's this squared, sorry, and then you add them. That's the Pythagorean theorem. Okay, so actually this is going to take even longer, right? We have to square this and then square this and then add them all together and solve there. And just quickly, it's going to look like, you're going to have 25 plus 10y plus y squared. And then this one's going to be 144 minus 24y plus y squared. You add all that up, it equals 169. And then you refactor it, and then that'll tell you what your solutions are. One of the solutions is going to be 0, and we just found that, right? We just found y equals 0. There's another solution that works too, though. And so we'll see that. And actually what it is it's 7. When you do all the factoring, simplifying, and then or all the foiling, simplifying, and then refactoring, you'll get 7, because if we add this 5 plus y, 5 plus 7 gives us 12. 12 minus 7, that gives us 5. So that's the textbook way. It takes a long time. So if we can think about this strategically, there's only one way to make this work if we have 13 as our hypotenuse here, for this to be equal to 90. There's only one other way. And so if we do that, we know that we've got to get this squared plus this squared equals 169. And then if you do that, you see that there are two values that work. right? Because you realize, oh, this, we've got to have a 5, 12, 13. That's the only way that this is going to work. At that point, then you know that there are other values that work, but that this isn't going to, what's going to happen to 13 is that this hypotenuse will get, for different values of y, this hypotenuse will get longer or shorter, and then x can't be 90 anymore. What I mean is as we change the Pythagorean theorem here, this hypotenuse can be this length, 13, if this is exactly 90. But if we're changing these side lengths, then the hypotenuse changes, and then this angle changes, and it can't be 90 anymore. And so that's why the answer is D. So because we know there are only two solutions, any other values of y that work are going to distort x. It's not going to be a right triangle anymore. We can put in side lengths that work, but they won't follow the Pythagorean theorem anymore, because the only two solutions that follow the Pythagorean theorem are y equals 0 and y equals 7. Does that make sense to everyone? Yes, no, a little bit. The idea is that the only way for x to be 90 is if it follows the Pythagorean theorem. There are only two values of y that work for that. Every other value of y that can still give you a triangle, it can still give you a true triangle. It's not going to give you a right triangle. All right. A construction company will produce identical metal supports in the shape of a right triangle, okay, with legs of length 3 and 4 feet. Kennedy, what am I about to say? What am I about to point out?
It could be a 3, 4, 5 triangle. Or is that one of them?
Yep. And I wouldn't even say could be. They said right triangle, and they said 3 and 4 are the legs. It's only, the only solution is it's a 3, 4, 5 triangle. The only solution. The three sides of each triangular support are constructed of metal stripping. If the company has a total of 6,000 feet and there is no waste of material in construction of the supports, what's the greatest possible number of supports that the company can produce? So Carson, do you want to tell me, do you see any ways to solve this one, to work with this?
Isn't it asking you for perimeter?
Yeah. Mm-hmm.
So because we know it's a 3, 4, 5, then we know that the perimeter is going to be 12.
Yep, the perimeter of each support is 12. So we'll put P equals 12.
And so then you just divide the 6,000 feet that you have in total by 12.
Yes. Mm-hmm.
So the answer is 500.
Right. Yep. And if we think about this, so this is a geometry question, but it's also an arithmetic question, in that it's a divisibility question, a factoring question. They're basically saying, which one of these is the greatest factor of 6,000 divided by 12, but we don't want to tell you 12 in a nice, easy way, so we're going to make you infer it from the 3, 4, 5 triangle. And so that's what they're doing there. Okay. The next one here. What is the area of triangle ABC shown above? Now, I see two angles. They gave us the measurement for two angles. It's worth figuring out what the third one would be. Jordan, do you know how to figure out what the third angle, so angle B in this case, because that's the one we don't know? how to figure out what this angle measurement is?
Yes, it's just 90 plus 30, which is 120, and then 120 minus 180. So then it would be 60.
Yep. And so, Jordan, what does it mean to you to see a triangle whose measurements are 30, 60, 90?
That it's a 3, 4, 5.
It's not a 3, 4, 5, but your mental map is very close to the right place. Let's go back. The 3, 4,
So
5 triangles over here. It's not a 45, 45, 90 or 30, 60, 90, but it is in the right space. So your brain is searching in the right area. But this is what we want.
So then they're all equivalent.
They're not all equivalent. I just grouped them as in like the Pythagorean triples are here and the special right triangles are here. These are the 4 types of triangles that you want to know, that you want to kind of quickly recognize. So this is a 30, 60, 90. The way I want you to break those down is if you can find the short side first, that helps everything else. So the short side is opposite the 30-degree angle, which means 6 is the short side. Okay, so the next thing I would do is say, okay, well, the short side times root 3 is my medium side. So this is 6 root 3. And then 6 times 2 is my hypotenuse, my longest side there. And so that's 12. So if I can find my short side, then everything else comes together on the 30, 60, 90. So at this point, we want the area of the triangle, right? How do we get the area of a triangle? Jordan, do you remember the formula for that?
I don't.
How do you get the area of a rectangle?
You just divide, or you multiply the base or the width times the height.
Yep, that is exactly right. And what I want you to remember, if you ever forget,
So then it would just be divided by 2. So that it would be the base or the width times the height divided by 2.
and we'll say times 1/2 it means the same thing, right? Okay, so then we do that. And I want to make my job easier. I'm going to do 6 times 1/2 because the order that you multiply doesn't matter. And since this makes my math easier, I'm going to do 6 root 3 times 3. That's going to give me 18 root 3. And so that's the area of my triangle. And just to quickly recap, Carson, I don't know when we lost you there, but if I see this is 30, Jordan noticed, oh, hey, we can subtract 180, subtract 90 and 30 from 180 to get to this angle 60. We now know it's a 30, 60, 90. The short side is opposite the 30. And once you know the short side, it's easy to get the rest of the triangle because you double it for the hypotenuse and you multiply it by root 3 for the long leg for the medium side. And now we can do 1/2 base times height up here. So 1/2 times 6 times root 3, or 6 root 3, and then you get 18 root 3. So what do you guys think of this one here? Does this look like anything we talked about?
We know they add up to 180.
Yep. So if we were to take your words, Jordan, and put them into math, we'd say add up to 180. That means R plus S equals 180. And then to follow up with what I said about how most geometry and data analysis questions are just arithmetic and algebra questions dressed up with a little bit of geometry or data analysis to kind of get you into the numbers that you need to use. What kind of problem is this once we get past the angles adding up to 180? Because I see this stuff. What's going on here? What am I looking at?
It's like algebraic proportion.
Yeah, it's an algebraic proportion. Yep. And how do we solve an algebraic proportion like this? When you have a proportion, let's say A over B equals C over D, cross multiply. So you get AD equals BC. Now, before you start cross multiplying here, Jordan did point this out. I think it would be nice to take out R plus S and substitute in 180 because I feel like that makes our job easier here, right? So I want you guys to try and finish that for me. Okay. Is anyone still working? Nope. Okay. Jordan, what'd you get for R?
I got, 1 second. I think it was, I just had it in my calculator. It is 112.5.
And that is right. So again, I don't want you guys to kind of turn your brains off to the arithmetic and algebra involved in a question. Once you see like, oh, there's some geometry in there. There's almost certainly going to be some arithmetic and algebra in there. And if we had decided, oh, it's a geometry question and that's what I'm going to think about, then we may not have noticed this here as a proportion. And if we don't notice that, then it's really hard to finish. You basically can't finish it without that. So you do need to realize, hey, this is a linear pair. R plus S is 180. Then you can do this here. That's going to be the way to solve it. Let's see. Do we have time to keep going? Yeah, let's stop here because this one's going to take a little bit of time. So let's take a break. We'll take a 5-minute break, come back around well, whatever time zone you guys are in, about 12 or 13 after. All right. Okay, let's get back to the GRE quantitative. Okay, so this is on page 205 in the workbook, and there we go. This is number 18 on page 205, so it's a mixed practice set. And we've got some coordinate axes here. Okay, yeah. And we've got points A and B are shown in the XY plane above. Point C is not shown. And it's on, let's see, point C not shown is above the x-axis, so it's above it. It's going to have a positive y coordinate, so that the area of triangle ABC is 10. Which of the following could be the coordinates of C? So I want you guys to spend a minute just thinking about, like, how would I try and do this? And one way to think about it is there are different directions you can work this problem. You can start with the graph and think about what you could do to get to the area of a triangle that's 10. But you could also say, hey, maybe let's start with the area of the triangle is 10 and work our way backward from that. So I want you guys to think about that for a minute. Just try some things out, see if you can come up with something, and then we'll talk about it. Okay. Kennedy, do you have any ideas?
Um, so I went from the area as 1/2 base times height and worked my way backwards since they gave us the area of 10 and line AB is 5. Is 6 minus 5.
So let's call that the base, right?
Yeah. So doing that math, I got H equals 4. So Y would need to be 4 in the solutions.
And you have done it perfectly. Which ones give us a height of 4?
A and D.
Yeah. And notice we have a box, which means more than one answer possible.
I think
And
you're displaying the wrong screen. Like, I see, like, I don't know if everyone sees it, but I see like
Okay.
the scoring charts for the 27.
Oh, yep, sorry. Let's fix that. Okay, sorry about that. Yep. Okay, well then let's do a quick recap of what Kennedy said. She's right here. We've got 1/2 base times height equals 10. We can fill in what we know. We know the base is 5 because they gave it to us. That lets us solve for the height is 4. And now our two answers here, since we have boxes for the answer choices, there can be more than one. And so the answers are both A and D. And what's a little bit maybe unintuitive at first is that this triangle has the exact same area as this triangle, because it's just about base times height. Those are the only two things that can determine the height of the triangle. Now you're doing it times 1/2, but you're always doing it times 1/2, so that part doesn't change. So just to kind of exaggerate it even more, we could have, let's say the height's way over here, or the top point of that triangle. Let's pretend I drew this a little bit better. All three of these have the exact same area because they have the same base and they have the same height. And so I think what we'll do is skip to, this is something from the big book. So number 18 here. So I'd like for you guys to just try and solve this one without me saying anything, and you'll probably notice like it's related to this number 18. So there's a hint, but I want you guys to try and solve number 18 here. Carson and Kennedy, it looks like you guys are writing. Jordan, are you thinking, or do you have an idea of what to do here?
I think you can just answer this without even doing an equation.
I agree. I see Kennedy and Carson writing though, and I don't want to stop them if they're calculating, but yes, there's a textbook way, and then there's a kind of quantitative reasoning way.
Yeah.
Yeah, I'm done. I was just like writing down so I'd remember the problem.
Okay. All right. So did anyone not get B? Everyone got B? Hooray. So this is integrating two of the things we talked about, right? Which is a triangle you can think of as just half of a rectangle where you do 1/2 base times height. Well, we did base times height in this case and we got 64. So that means the area of the triangle is going to be 32. So this area is 32. I don't expect, this might be something you see kind of knowing this. I do not expect that you'll have to know this, but if you guys think about it, like this triangle plus this triangle also has to equal 32, right? So the green area is 32 and the blue area is 32. Okay. So it looks like everyone kind of understood that. That's great. Let's do number 13. And instead of showing you guys how to do it, I'm just going to refer back to its cousin. This is a less evil version of number 4 here. So if we look back at what we did at number 4 on page 88, that is a tougher version of number 13. This is a quantitative comparison one when I was cutting and pasting quantity A, quantity B. That part got cut off. And this one, I would say the textbook way, it's hard to even really think about what that would be. I guess we could, no, it's tough to think of a good textbook way for this one. This is definitely a primarily quantitative reasoning one. Okay, Carson, do you want to talk to me about how we can solve number 13 here?
Yeah, so I guess what we'd be asking you for in theory are like the comparative parts of the Pythagorean theorem.
Perfect, yep.
But that would be assuming that RST is a right triangle, which you don't know. So you can't say definitively if it's true or not.
Yeah. Right. So we can't say. If they had said that it's drawn to scale, let me go back to it and see. I don't think I left any text off. I don't think I cut anything off, but I'm just going to check to make sure. But Carson, like you said, if they don't tell us, we don't know. And so all we can say is the relationship is unclear. Yep, they didn't give us anything, so we don't know. Now, what if they did say this was drawn to scale? What could we say? Could we say something about RS squared plus ST squared versus RT squared? And I'll put a question mark here because we don't know if that's true. What if they did say that this figure here is drawn to scale? What would we know? We would know that this angle is bigger than 180. And if this angle is bigger than 180, that means that it's opened up this side to where this side is longer. So if this is bigger than 180, then RT squared is greater than RS squared plus ST squared. Another way to think of it is a perfectly 90-degree right triangle perfectly fits the Pythagorean theorem. If we make this angle bigger, let's exaggerate that more. By making this angle bigger, this side has to get bigger. And so then we get a squared plus b squared is less than c squared if this angle is greater than 90. And then if we make it smaller than 90, then that means a squared plus b squared is greater than c squared. So that's kind of just knowing what happens when you stretch a triangle so that it no longer fits the Pythagorean theorem. If you make this angle bigger than 90, c has to get bigger. If you make this angle smaller than 90, c has to get smaller. All right. These next ones, we may have done these for homework. So if we have, let me know, take a look at them real quick. And if not, then we can do them together.
Can we just do them?
Yeah. So I'd like you guys to try, definitely, let's just try number 7 first. So we have quantity A and quantity B. So it's a quantitative comparison. This one integrates at least three, no, at least two of the angle rules that we talked about. Okay. Did anyone get an answer for this? Jordan, what did you get here?
I don't think I did it correctly. So
Okay. Talk to me about what you did.
okay. So T equals 50, which means Q equals 50,
Agreed.
which means M equals 50.
Good so far.
And then R equals 50.
Uh-huh.
So then, actually I did do this. So then S is 80, and
Why is it 80?
because it equals 180.
Because QRS, right, all the way around.
Right.
Since this is a baseline, since this is a straight line, they have to add up to 180. So yeah, so that's 80. And then also V is 80, right?
Right.
Okay.
So then QR is 100, and then S is 80. So Q plus R would be bigger.
Yes, correct. All right, number 9. I'll give you some hints because this one is a little bit tricky, but we have PR as the diameter of the circle. Okay, QR is tangent to the circle. One thing I want you to notice is when you have a line tangent to a circle, it always hits the diameter at a right angle like this. Now they told us that, so that's nice, but they may not always tell you. So a tangent means that it hits the circle at one point, and then it also means that it hits a diameter at a right angle. Now, that means we've got a right triangle here, right? PQR. That's a right triangle. And then they want the length of PR. And then they want the length of QR. Well, what formulas or what math can we use to get the length of the sides of a right triangle? We need the Pythagorean theorem, right? A squared plus B squared equals C squared. So if we want to try and solve this, we need that information. Another possibility could be maybe, if we knew something about the circle, we could say PR. We could figure out what PR is because it's a diameter. So if we knew the radius, we could double it or something like that. So we don't really have that here. If you notice, we just don't have any side lengths. We can't really do anything here. So we know it's a right triangle. And one way to think of it is if they gave us just a little bit more info, we could say a lot about this, but we just don't have it. So I think I'll just give away the surprise, and we just don't know. QR could be much shorter, much longer. We just don't know. You could have a situation where the diameter is much longer than QR, and so you get a triangle that looks like this, or you have a situation where the let's move that, where the diameter is a lot shorter. And then you get something like that. So it could be either way. We just don't have any values to say. All right. Looking at this one here, we've got number 2. These are both from the big book. X plus Y versus Y plus Z, another quantitative comparison. And then we've got number 7 here. We've got the length of RT, so that's here. And then we have twice the length of RS, so that's this side length here. And I want you guys to try and solve both of these. Let's see how we're doing on time. Yeah, we're okay for time. So I want you guys to try and solve both of them. Again, think about what questions these are like, what geometry rules we can use to set them up. So I'll give you guys a couple minutes. If you can do both, that's great. If you can only get through number 2, then we'll go through that, and then we'll go on to number 7. Okay. For number 2, Jordan, what did you get for number 2?
I got they're equal, so C.
Okay. And how did you get to that?
Because XY equals
X plus Y.
X plus Y equals 180, and
Good.
then Z equals X. So there.
Yeah. So you can say, hey, they're both equal to 180. You can say x plus z is equal to 180. And you can also say x plus y is equal to 180. Or you can say, hey, I can substitute in, since x and z are equal to each other, I can substitute in this for x, and then so there are kind of two ways to show that. Good. Okay. Let's look at number 7. So we have the length of RT versus twice the length of RS, and RSV or RSTV is a square. So we can kind of reason our way through this, but we can also prove the exact relationship between them. What I'm going to do is I'm going to say that the length of SR or RS is equal to S. The length of ST is also S, right? Since it's a square, let's call every side S. Okay. If every side is S, I want you guys to figure out exactly what TR is equal to. It's going to be something with S in it. Kennedy, do you have any ideas for solving for TR or RT?
Isn't that S to the square root of 2?
Yep, because we got a right triangle, right? S. So we have S squared plus S squared equals 2S squared. And so we square root that and we get S root 2. Now, if we know that cutting a square diagonally makes a 45, 45, 90, then we can just say, oh, this is S, this is S root 2. And then we can say, well, S root 2 versus twice the length of RS. Well, that's 2S and then S root 2. Root 2 is about equal to 1.4. So the bigger quantity is going to be column B.
Couldn't you just reason your way through that too?
For sure.
Like,
could you explain to us how to reason through this one?
yeah. I mean, if RS, I'm going to try and say this smoothly, not just what's jumbled in my head. So if RSTV is a square and twice the length of RS, which is one side of the triangle, and you cut the square in half, which gives you TR, like RS and ST have to be more than TR. So you probably have a much better way of explaining it, but I feel like that's very straightforward.
7 o'clock. What you said is exactly right. There's a special thing for it called the triangle. Sorry, I just lost my train of thought. I think it's the triangle inequality theorem. It basically says that if you have a triangle, doesn't have to be a right triangle. We'll call this A, B, and I don't want to say C because we're implying then that we've got a Pythagorean theorem here, so because we don't know that this is 90. A plus B has to be greater than D. If D gets too big, you can't close the triangle anymore. It just flattens out, right? As D gets bigger, the triangle gets flatter. Well, at some point, if D gets too long, it just flattens out into a straight line because A and B have to like collapse. And so what you said is exactly true. TR has to be greater than ST and SR, but it can't be too much greater. It can't be double. It can't get to the point where it's equal to the sum of these two.
And if they said RSTV, if they implied that it wasn't a square, then you couldn't complete the problem, correct?
You'd still know the triangle inequality theorem would be true. You just don't know like ST compared to SR, but you do know that, if they'd asked you just for twice the length of RS, then potentially, yeah, you'd say D, that you
Okay.
can't tell. Because what if RS is the short side, or what if it's the long side? You don't know.
Right.
Yeah.
Okay.
All right. This next one here, I think this is 1061. So this one here, it's not super hard, but you got to use a few different things here. And so I'll give you guys a little hint. Do you see how we have triangles inside of triangles? A lot of times it helps when you have this to think of them as like separate triangles that you're going to take apart. And what I mean by that is, in my head, and maybe even on scratch paper, I'm going to make a triangle that does this. It says 16, here's the right angle, and here's 20. I'm also going to rotate this one so it's easier for me to deal with and say, okay, this is now my side 20. The bottom is now X, and the long side is now 25. And then there are multiple ways to solve this now. And one thing I would look for is, I wonder if there were any ratios I simplified by that would allow this to be one of the Pythagorean triples that we run into a lot. Okay, let's start with, does anyone see a short way, the shortcut to finish this one?
The whole triangle is a 3, 4, 5 triangle, isn't it?
The big one, right? It is. Because if we divide this by 5, if we divide everything by 5, then we've got a 5 and a 4 here, which means this has to be a 3. And let's say 3 times S, so we'll say side, right? That tells us our ratio, right? So if we divide everything by 5, then that's what we get. So what does X have to be if this is the case? Or actually, I'm not going to use S because it looks too much like a 5, and I actually want to use a 5 here, so we're not going to do that. Right, we realize, hey, we're multiplying everything. If we divide everything by 5, we get back to our 3, 4, 5 ratio. So let's multiply everything by 5. X has to be 15. Does everyone see that? And just to show you that there are multiple ways to solve these questions, so they come up, again and again, you can also say, notice that here, this 2016, this is also a 3, 4, 5. Check them and turn it down a little bit. And so this is a 3. And since we multiplied everything by 4, that makes this a 12, which means this is a 12 over here. And then if we do that, we've got a 9, 12, and then we can use the Pythagorean theorem to solve for this. And if we have a 9 and a 12 and an x, we divide by 3 and we see it's 3, 4, 5. So we do that 5 times 3 again and we get x equals 15. So there's definitely a long way if you don't see the short way. But if you can think of this as 3 different triangles, and this is a pretty common triangle setup here. If you can think of this as 3 different triangles, then you can look at each one and figure out which one is the best one to play with. In this case, it's the big one. Sometimes you might want to play with, we'll just say like, you want to start here with this one. Or you might want to start with this little one here, or the medium-sized one. But just realizing that you can do that and then choosing to draw them away from the main figure so you can kind of visualize what's going on better, that can help you see the shortcut quickly on these. So anytime triangle inside of a triangle, I also see them sometimes like this, where you have this is a parallel line and then this is the base, so that kind of triangle within a triangle. A lot of times I'll turn it into here's the big one, here's the little one, just to help me visualize or kind of conceptualize what I'm supposed to do. Okay, so that's it for today. I think, we've gone through everything. You might want to refresh yourself with the geometry notes that we did. These are things that you'll want to come back to. But that covers, a lot of ground for what you're going to be doing in the triangles here, or for the geometry here, and a lot of it has to do with triangles. There's a little bit of stuff with circles, and we'll do some of that on Wednesday. But really, if you can do triangles and circles, then you're going to be in pretty good shape for the GRE geometry. Does anyone have any questions? Okay.
Not that it will, if it happens, great. If not, but did you say you'll be sending an email if Wednesday does get rescheduled?
What I'll do is I'll send an email to you guys, and then you guys can reply with, I'll give you guys some options for meeting at a different time, and then we'll see if maybe later in the week or something like that. Just quickly, Kennedy and Jordan, are you guys available? Let's say like on a Friday or something. You are, Jordan?
Yes.
Okay, and you are, Kennedy?
Yeah, any other day would be fine.
Okay, and then what
Same.
about you, Carson?
Pretty much any day after 5 EST works for me.
Okay, so let's shoot for Friday then. I'll send out the email just to make sure, because you guys may look at your calendar and realize that you had something planned that you didn't remember, because that's what I always do. I agree to things without looking at my calendar, and then I'm wrong. And I should probably even check myself. So I'll do that, and then we also want to make sure Mara can be there on Friday. So I'll send out the email. Everyone double check, make sure you're good, and then later tonight I'll send the video and the notes. And I don't remember who was here when I said it, but what I'm going to try and do is upload all the videos I still have of our classes to YouTube, and then send you guys the links, because the Zoom cloud recording is limited. It has limited space, so I've already had to delete a couple classes, and I'd like to keep as many of these up for you guys to go back to as possible. All right, so then I'll see you guys probably on Friday.
Thank you.
Okay, all right, bye.
Thanks.